Hi. In this video, we are going to explain 3 examples as application to planar kinematics of a rigid body. In the example in front of us here, we have a cord is wrapped around a wheel, which is initially at rest. Okay. What does mean at rest? It means, let's find that means omega naught is equal 0. And when theta is equal 0. Okay, so theta naught is equal 0. If a force is applied to the cord and gives it an acceleration a equal 40 meter per second square, so that would be the tangential one for the point B is equal to 40 meter per second square. How I know it's tangential? Because the unit is also given meter per second square, not radian. All right. What else? Where t is in second, determine as a function of time the angular velocity of the wheel. They want the angular velocity of the wheel, omega, and they want to find the angular position of line OP in radian. So they want the angular velocity and position. All right. So that's the information given. And the radius is given on the graph here, 0.2 meters. So just let's write the r is equal 0.2 meter. So that's the information. Well, what are the most important equation that's related to this one? The tangential acceleration just equal to angular acceleration times the radius, and the angular acceleration is equal the rate of change of the angular velocity, and omega is equal to the rate of change of the angular displacement over time. This, I think, the basic equation that I remember that maybe is related to this example when I read it. All right, so let's just start and tackle the problem here. First of all, they need to find the angular velocity, which is the omega. How we find omega? All right. So omega can be found if we know the acceleration, because we know that alpha is equal to d omega by dt. This is one situation. So I need to know alpha. Okay. But alpha is not given and at is given. So I ask myself if there's a relationship between the angular acceleration and the tangential acceleration. Yes. It's here. This is given here. The tangential one is equal the angular acceleration times the radius. So I'm going to use this one. So I will say that the tangential acceleration of point P on the disk is equal alpha r, and so alpha will be equal to what's alpha angular acceleration is equal tangential acceleration divided by r. And the tangential acceleration is given here is equal 4t divided by the radius, which is equal to 0.2 meter. So we get 20t radian. That's radian per second square. So this is alpha. All right. We got alpha, and we know that alpha is equal to the first derivative of the angular velocity with respect to time. In this case, we'll say that the d omega t is equal alpha. I multiply by dt both sides, so that's d omega, and then I integrate both. Integrate the omega from initial angular velocity up to omega, and this one from time equal 0 up to t. So let's just do this integration. So the first one, the omega will be omega minus omega naught, but omega naught is equal 0. It's given here in the problem, is at rest, equal alpha. Alpha, this is alpha, I just got it, is equal to 20t. I'm integrating this from 0 to t. So omega will be equal to 20 is constant, t will be t squared over 2 from 2 to 0. That will be equal to 10t squared. So I found expression for the angular velocity, which is equal to 10t squared. And of course, the unit will be radian per second. So that will be the angular velocity. Well, now I want to find the displacement. Do you want to find the displacement? So I know that omega is equal to d theta by dt. I'll do the same thing. So d theta is equal omega dt, and I'll integrate both. That's from the initial position to any position from 0 to t. Initial position was given to 0. Okay, that's easy. So I have integration from 0 up to theta equal to the integration for omega. I just got omega 10 t squared. So that will be equal to 10 is a constant, t squared will be t cubed over 3, and the integration from 0 to t, that will be equal 10 over 3 t cubed. That's the theta. So let me just write theta will be equal to 10 over 3 t cubed. That's the angular displacement in given, of course, in radian. Well, why did that? I didn't use the equation that said omega equal omega naught plus alpha times t, because it's not constant acceleration. It's function of time. See, when it was given at the beginning here, it said at is equal 40. I got alpha is equal 20t. If it was 20, I'm going to use the equation for constant acceleration, but that's why I didn't use. I use just integration and differentiation. All right, let's go to the second example. That's a simple but nice one. Has also a different idea. It said here that a table fan rotating at a speed of 2400 revolution per minute is switched off. So switch off. When switch off, and the resulting variation of revolution per minute with time as shown in the figure. So obviously it starts here like 2400 revolution per minute, then start to decrease to 1000, and then decrease to set at rest. Determine the total number of revolutions. How many revolutions? Okay, the fan has made in 25 seconds, because it has 10 seconds, it would follow one path, and then from 10 to 25 another rate of change when it finally comes to rest. Okay, well, it's a simple problem actually, but just how to find the solution, we got to know the basic rule we need to know here. Obviously it's like the speed is given in as revolution per minute. So we got revolution per minute, it's angular velocity, but not radian per second. So we got to change from revolution per minute to radian per second. This is the first thing, just I thought about it. So let's give it, we'll call it N. N is the revolution per minute. All right. What does it mean, revolution per minute? It means in 1 minute, for example, 2400 means in 1 minute to make 2400 revolution. What's revolution? Revolution is like make one turn. All right. So one revolution is equal, as you said before, 2 pi. All right. So when you say have n revolution, if you have 10 revolution, you multiply by 2 pi, you get the angle, right? So when you multiply the number of revolution by 2 pi, you get the angle theta itself. Per minute by time, it gives you speed. You see, so you will say that if you multiply 2 pi by n, you get the angle, and divided by time, because this is per minute, so you want per second, so you divide it by 60, because 1 minute is equal to a second. That will give you the angular velocity. So that's how you turn from revolution per minute to radian per second, because you turn 2 pi n become radian, and then the 1 minute equals 6 seconds per second. So that's actually how we do that. Well, so actually you can say that omega is given in this diagram, omega against t. What's required? We need to find that how many revolution it will make till it rests, stop moving. What is the relationship between displacement and, because to find the number of revolution means how many radian, it means that you want to find theta. We know that omega is equal d theta by dt. That's the equation or the relationship between the angular velocity and the angular displacement. So this is the equation we're supposed to. So you want to find theta. So you'll say the delta theta would be equal omega delta t. And then you make the integration you integrate the d theta, that's from 0 up to theta, so theta. And then what about the omega? Omega dt, you are integrating with respect to time, is from 0 up to 25 seconds, right? But what do you have here? Omega, it has a relationship with n, right? So you will say integration from 0 to 25, that's the time, second, and omega, we just got it in this equation, to 2 pi n over 60. So theta will be equal to the integration from, let's just get the constant out. So theta will be equal to 2 pi over 60. I'm just looking at this equation, this one. 2 pi over 60, that's constant, and the integration will be only for n. So from 0 to 25 n dt. So what does it mean, the integration of n? That is n. That's given revolution per minute in this diagram. That's n. I call it n, revolution per minute. So when you integrate with time, it means you find the area, right? So I will find the area. I'm not going to find the equation and then it'd be a long way, especially when you have this kind of geometric. So I want to find the area of this triangle, and I want to find the area of this rectangle, and I want to find the area of this triangle. So in this case, I add the all areas, so it means I did the integration here, all right? So that turned the problem to an easy problem here. Well, so what is the area of the triangle? You have from 0 to 10, so the base here is equal 10, and the height from 1000 to 2400, that will be equal to 14, right? So let's just do the area here, 0, 25n dt, that's equal the area under the curve, under the nt curve. So the first one will be rectangle, that's 1400 times 1 times 10, I'm sorry, that was 10, from 0 to 10, that's right, divided by 2. That's the area of the triangle. The other one I have rectangle here from 0 to 10, 10 times 1000, so 1000 times 10. And the last triangle from 10 to 25, that's 15, and the height is equal to 1000. 15 times 1000 divided by 2, and I get this area. Let's just do the area, then it's equal to 4500 radian. Okay, no, that's not radian, that's revolution per minute, revolution per minute times second, because I did the area like that. I have a constant here that will fix everything, that 2 pi over 60 will fix that. So now I can say that the theta is equal to 2 pi over 60. I'm just looking at this equation that I found. 2 pi times the integration, which is the area I just got. So I have 2 pi over 60 times 24500. It will give me in radian. Okay, let me just calculate this one, see what we get. I have 2 times pi times 24500 divided by 60. That will give 2565.6. All right, radian. And let's continue here. So we know that we want to know how many revolution you can get. So we'll say that one revolution makes 2 pi. So that's the theta that you got in radian. You got in radian. So how many revolution you will get till stop? Okay, I want to find the number of revolution. So I will just say n. I want to find n, the number of how many turns or revolution the fan will make before it stops. So making this, so n will be equal theta, and then I got and divided by 2 pi. So you get this result and divided by 2 pi, and you get the value whatever you can get from this one. 2565.6 radian divided by 2 pi, and you get the number of revolution that will stop. Let me just calculate it here for you. That's 256.5 25 missing number here. 5.6 divided by 2 pi. That's equal to 408.3. So you can say it's 408 revolution, and then it will stop to make this number of revolution. So it was an easy problem, but it's a good application, you know, how to find how to use the area instead of integration to find the number of revolution. So that was a simple problem, but it's really good. Let's find the last one. That's the third one. That's an interesting one. We have also here motion will be transferred through the gears. That's interesting. Like the one we did in the last video, we used the belt. So now that the motor turns gear A with a constant angular now constant angular. Just let's mark this constant angular acceleration. All right. So maybe we use okay. And the acceleration of A, it's equal to 4.5 radian per second square. So that's angular acceleration because by radian, okay? So that should be clear like alpha, it doesn't look like it. Starting from rest, so that's also another information we have here. The cord is rigidly attached to gear B. It means that will be transferred. The velocity, remember another, the velocity will be the same, tangential acceleration will be the same. Find the velocity of the cylinder C, which is one. You want to find the velocity. And the distance that the cylinder C travels in 3 seconds. Time is given. All right. So let's just write the information that we have here. Well, what's given? Alpha is given. Alpha of A is given 4.5 radian per second square. The radius of A is given, or not? Yes, it's given. RA is equal to 75 millimeter. RB, everything in A is given here. Now we'll go for B. B, you got to look at B here. We have that's the poly, which has the radius 125, and you have the gear B. So you have A, B, C, D. All right. So RB, which is the gear, is equal to 225, and RD is equal to 125 millimeter. Okay. And also it said start from rest. We got to remember this condition, which means that the velocity was 0 in the beginning, obviously. All right. So I think we did everything given here. All right. Let's now start. It's interesting to know, first you look for the transmission system in the gear. When you have gear, and this gear is just the tooth of the gear there, and in this tangent plane here between them, they have is like at the point where gears A and B mesh, the velocity will be the same, tangential acceleration will be the same. So let's write this at the point where these two gears, this is gear A and this is B, where gears A and B mesh, what happened? The velocity will be the same at this point of tangent. So V A, it's linear, of course, motion V A and V B, the linear velocity, and the tangential, it's also the linear part of A, should be equal the acceleration tangential component of B. That's important. Always you look for this condition because it will make the problem easy. All right. So now what we try to do, we try to find alpha of B, because we know already alpha of A, so we need to find alpha of B. So that's the first unknown we'll try to get. How we'll get it? We are going to use, you know, this information that we get it from the transmission. All right. Because we know that the acceleration, they are equal, what's the relationship between the tangential acceleration and the angular acceleration? It's equal alpha r in general. So we'll say that A, the acceleration tangential of A, tangential is equal alpha A times RA. Because I have the alpha A is given here 4.5, so I have 4.5, and RA is given 75 millimeter. I got to convert it to meters, so I divided by 1,000. Don't forget that. So I get the acceleration, which is the tangential component. Of course, I get it here. All right, so I'll just leave it like that. I know that B tangential should be equal A tangential. I know that. So I will know it's equal to whatever I have here at the top, 4.5. Let me just calculate it. Okay, don't be lazy. 4.5 times 75 divided by 1,000, 100. Okay, that's equal to 0.3375 meter per second. 0.3375 meter per second, and I know that the acceleration is equal alpha times r. Now I'm looking for B, gear B, alpha B, and the RB is given here 225 millimeter, 225 millimeter. So the acceleration, angular acceleration of gear B will be equal to 0.3375 divided by 225. Don't forget to divide it by 1,000 to meter, and the value of the alpha beta will be equal approximately 1.5 radian per second squared. So I got the angular, let's just like not forget that the angular acceleration of gear B. All right, let's go back and look at the problem here. It's interesting, another connection here. Let me make it bigger to just see it. The pulley D and the gear B. Pulley D is attached. It's attached, you know, with the core of the gear B. So it means everything happening with the gear is the same as D. So the acceleration of B will like the acceleration of D. I'm talking about the angular because they have the same axis. They are rotating about the same axis. So they're having the same angular quantities. All right, so let's just do that. That's important. You see, it's different between the two gears mesh. You talk about linear components, which is a velocity, linear velocity V, and tangential component only. But when you talk about something have the same axis, rotating on the same axis, they got the angular quantities are equal. Okay, that's an important observation. So just if I just a sketch, just to show you, this is D, the pulley, and then you have the gear, B. Just to make it, this is gear and this is brake. So we'll say gear B and pulley D turns together. Yes, it turns together. So what we conclude that the angular acceleration B, it's equal angular acceleration D. All right. Do we know any acceleration here? Well, I think we got the acceleration d here. Yes. So acceleration d will be equal to acceleration b, which is we obtained 1.5 radian per second square. All right. So we got AD. Well, now I'm going now to the cylinder C, because the cylinder C, as you see, it's just connected to the pulley. That's why I was focusing on the pulley. Okay. So now I want to find the velocity of the cylinder and the acceleration of the cylinder for tangential. We have to mention something, the assumption that about the connection between the cylinder C and the pulley B with this cord. So what to do the right solution, we should say the following, assuming, because what we are doing now doesn't apply for every single condition, assuming the cord attached to pulley D will assume two things important. Inextensible, it means it cannot be like it's not like a rubber will be extended. No. It can be with just the length will be fixed. It doesn't change with the load, and doesn't slip, because if it slips, it will change everything. The speeds will not be the same from the top from the pulley to the cylinder. Doesn't slip. We have these two conditions, so we can say the following: the velocity of the cylinder C equal the velocity of the pulley, and the acceleration also. This is one. Always good about the acceleration also, and the acceleration of cylinder C, of course I'm talking about the tangential because this is moving linearly, equal the acceleration of the pulley, the tangential component. All right, they are not on the same axis. They are there is transformation. So when there is transformation, we talk about tangential component, linear component velocity, tangential component of the acceleration. Okay, so doing that, so we got to find the acceleration of D, so we can get the cylinder C. The acceleration of D, I'm talking about the tangential component, you know, it's equal alpha R. So we use alpha D and RD. Alpha D, we got it. If you remember, we got alpha D is equal to 1.5 radian per second. And RD is given. RD is given 125 millimeter. Divided by 1,000 to get the acceleration tangential component of that will be 0.1875 meter per second square. Great. Now I can say that the acceleration of the cylinder C, the tangential component, of course, that's equal to the same thing of the pulley, which 0.1875 meter per second square. And it's going upward, it's following it. Since alpha A is constant, remember, that was mentioned as constant. Let me refresh your memory. The motor turns gear A with a constant angle acceleration. So alpha A is constant. So if alpha A is constant, the acceleration is constant, so the angular acceleration also of D and C constant. They are all connected. So what do we need? What the equation we're going to use? The equation for constant acceleration. Once it's mentioned, so we just use it. Easier. We're not going to integrate anything like that. For constant acceleration, the velocity, the linear velocity is equal initial velocity plus acceleration times t. And the displacement is equal to VOT plus 1/2 AT squared. That's for constant one. So now we'll go for the cylinder. For cylinder C, which is moving linearly, vertically, if you look at it. That's why I'm using the linear motion, because it's moving down. It's not rotating. So the velocity will be for the cylinder will be equal v naught plus at, and v naught is equal to 0 start from rest. What about the acceleration? We just got it. The acceleration AC, we got it here. 0.1875. And the time, 3 seconds. So it's given 0.563 meter per second. So we got the velocity of the cylinder. What next? They need to find the displacement, how far it will go. So that's delta S. Will be VOT plus 1/2 AT square. Initial velocity was 0, so you have 1/2, and the acceleration we have it again 0.1875, and the time is equal 3 seconds, and just to get the displacement 0.844 meter, and it's going up. So that's it. So it's solved, and we use different equation here, but it's very important to focus on how the connection of transmission system, and I will just again before we leave. So if the gears here, where they mesh, the linear components are equal, velocity and tangential component acceleration. When you have the pulley fixed on the same axis of the gear or whatever rotating with, they have the angular quantity are equal, which would be the angular acceleration and the angular speed, and that's it. All right, we're done with the part of the rotation about the axis, and see you later.